Hello everyone! This video is entitled VSEPR Theory and Molecular Shapes. VSEPR theory, otherwise known as valence shell electron pair repulsion theory, is a widely used model in chemistry that predicts the geometry of molecules based on the number of electron pairs that surround the central atom. This theory is based on the principle that valence electron pairs repel each other and therefore adopt an arrangement that minimizes repulsion, ultimately determining the molecule shape. This lecture provides an in-depth exploration of this topic and highlights the crucial role played by molecular shapes in various chemical reactions and biological functions. If you have not yet watched my video on Lewis structures, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started. Proposed in 1957 by Canadian chemist Ronald Gillespie at McMaster University, this theory is a model developed for predicting the shape of molecules due to electron repulsion. The fundamental principle of this theory is that the bonding pairs and lone pairs of electrons in the valence level of a molecule repel each other. This causes the orbitals in the molecule to position themselves away from one another so as to minimize the forces of repulsion between electron pairs. This decreases the molecule's overall energy and increases its stability. A lone pair, signified by the letters LP, will repel more than a bond pair signified by the letters BP. Bonding pairs are localized between the atomic nuclei. The positive charge of the nuclei keep the electrons restrained to a smaller area and counteracts the negative charge these electrons radiate. This thereby reduces the repulsive force. So bonding pairs will repel less and spread out less than lone pairs. Therefore, bond pair repulsions are the weakest within a molecule, and lone pair repulsions are the strongest, while the repulsion between a bond pair and a lone pair is moderate by comparison. This scale on the right outlines the levels of repulsion between these electron pairs, from weakest to strongest. Since Professor Gillespie's publication, a great deal of imagery has been done to substantiate his theory. The suggested three-dimensional arrangements of atoms and molecules using VSEPR theory was evidenced by experimental methods such as X-ray crystallography and nuclear magnetic resonance spectroscopy. The significance of Ronald Gillespie's discovery cannot be overstated. It is because of his simple yet brilliant observations that we now better understand how and why certain compounds react and connect the way they do. Additionally, his theory has helped us to better understand why certain enzymes only seem to work when they interact with particular compounds. We now know that enzymes are very large molecules folded into complex three-dimensional shapes. They have these active sites, which are empty spaces within the molecule that only allow for compounds of an exact shape to fit within them. It's very similar to a lock and key mechanism. There are two main categories for VSEPR shapes. The first category is the geometrical electron group arrangement. These shapes are based on the position of valence electron groups that are bonding or non-bonding around the central atom. This category is called a group arrangement because each single, double, and triple bond is treated the same. Every kind of bond in the molecule is considered to be a single group of electrons. So an electron group can be one pair of electrons, a single bond, or as many as 3 pairs of electrons, a triple bond. Because this category is concerned with the arrangement of electrons around the central atom, and not the bonded atoms, it is oftentimes considered a broad classification, under which compounds can be subdivided into molecular shapes. This brings us to our second category of VSEPR, molecular shape. This category refers to the relative position of atoms in the molecule rather than the electron groups, and is determined by the angles between the bonded atoms. What sets this category apart is that lone pairs are not considered when describing the shape of a molecule. Let me use this slide to clarify. This table shows the 5 geometrical electron group arrangements that you're required to know. The shapes of those geometrical arrangements are shown here. The first of these shapes is called linear. It has two electron groups that are separated by 180 degrees. The second is called trigonal planar. It has three electron groups that are evenly spaced apart into this triangular shape. The third is called tetrahedral. It has four electron groups that are arranged into what looks like a tripod. The fourth shape is called trigonal bipyramidal. It has five electron groups that are arranged into what looks like two triangular pyramids that are stacked one on top of the other but base to base. And lastly, we have the shape octahedral. It has six electron groups and is called octahedral because the electron groups are arranged into a shape that has 8 sides. So if these are geometrical electron group arrangements, what are molecular shapes? Well, first it's important to note that the same geometrical electron group arrangement can have more than one molecular shape. Let's take another look at trigonal planar. Trigonal planar has its geometrical electron group arrangement based off of its three electron groups taking this triangular shape, hence the name trigonal planar. But it's important to note again that molecular shape is based off of bonded atoms. And so if I were to name the molecular shape here, I would also name it trigonal planar because the bonded atoms are taking the same form as the electron groups. But what if I were to convert one of these bonding pairs to a lone pair? Well, in this situation, the molecular shape is no longer taking that triangular form. It looks more like a bent stick. And because of that, the molecular name is now bent. So although this compound now has a lone pair, it still has three electron groups, two bonding and one non-bonding. And so because of that, it still holds the same geometrical electron group arrangement, which is called trigonal planar. But the molecular shape now is called bent. So in fact, this category of electron group arrangement can have two molecular shapes. It can have a bent shape, or it can have a trigonal planar shape. There are 5 rules when it comes to drawing VSEPR shapes. The first thing you need to do is draw a Lewis structure for the molecular ion. Second, count the total number of electron groups, bonding and non-bonding electron pairs around the central atom. Third, identify the most stable arrangement for the number of electron groups in the compound by referring to the table of electron group arrangements that I showed you in the last slide. Fourth, determine the position of the atoms based on the type of electron pairs, whether they are bonding or non-bonding pairs. Remember, the goal is to arrange the electron pairs as far away from each other as possible so as to minimize electron pair repulsion. Take CH4 for example. The VSEPR shape would look something like this. You can see that the bonds to hydrogen are arranged as far apart from each other as possible. The shaded triangle means that the bond is coming out of the page towards you. The dashed line means that the bond is going back into the page away from you. And the solid straight line means that the bond is in the plane of the page. And the last rule is to identify the molecular shape based on the positions of the atoms, not the electron pairs. Let's take a closer look at the molecular shapes of compounds with different geometrical electron group arrangements. So this slide will show that there's only one possible molecular shape for a compound that has 2 electron groups. The geometrical arrangement of 2 electron groups will always create a linear molecule. The electron pairs within those groups will always be bonding. This creates 2 regions of high electron density around a central atom. If the central atom is where my laser pointer is, these balloons are drawn to represent the orbitals that house the electrons between bonded atoms. A general representation of this type of compound is shown here, where A represents the central atom and the X's represent the peripheral atoms. An example of a linear compound would be beryllium dichloride. Now I know what you're thinking. You're thinking beryllium and chlorine, that should form an ionic compound. But in fact, if you look at the electronegativity of beryllium, it's 1.5. And the electronegativity of chlorine is 3. So the difference actually provides you with a polar covalent bond, not an ionic bond. And so that's why you would see a compound such as beryllium dichloride in a VSEPR package. If you take a look at the compound, it's clearly linear because the two chlorine atoms are separated by 180 degrees. There are no other possible molecular shapes due to the fact that both electron groups must be bonding to a central atom. Otherwise, you would not have a central atom, and this would not be a VSEPR structure. The next geometrical arrangement is of 3 electron groups and takes the name trigonal planar. There are 2 possible molecular shapes for this geometrical electron group arrangement. The first has 3 electron groups bonding to atoms. Because of this, the atoms will be arranged in the same triangular shape as the electron groups, and so the molecular shape will also be called trigonal planar. This image shows the 3 regions of electron density pointing as far away from each other as possible. The general representation of this shape is shown here, where A again represents the central atom, and the X's represent the peripheral atoms. An example of a trigonal planar compound is boron trifluoride. The boron trifluoride molecule has 120 degree angles between all the electron groups. So that's 120 degrees between all of these fluorine atoms. The second possible shape has 2 of the 3 electron groups bonding to atoms and 1 non-bonding group. This gives the molecule a bent shape. This image shows how the lone pair repels more than the bonding pairs, pushing them closer together and further away from itself. The general representation of the shape is shown here, with the E representing a lone pair and the yellow sphere representing a lone pair on the compound. An example of a bent compound is the nitrite ion. This ion has angles greater than 120 degrees between the lone pair and the bonding pairs, and an angle less than 120 degrees between the bonding pairs. This occurs because the bonding groups are pushed closer together by the stronger repulsion of the lone pair. The next geometrical arrangement is of 4 electron groups and takes the name tetrahedral. There are 3 possible molecular shapes for this geometrical electron group arrangement. The first has all 4 electron groups bonding to atoms. Because of this, the atoms will be arranged in the same arrangement as the electron groups, and so the molecular shape will be called tetrahedral. This image shows the 4 regions of electron density pushing as far away from each other as possible. The general representation for this shape is shown here. You can see that it looks similar to a tripod for a camera. An example for a tetrahedral compound is the ammonium ion. This ion has 109.5 degree angles between all of the electron groups. So every one of these hydrogen atoms is bonded exactly 109.5 degrees away from each other. The second possible shape has 3 of the 4 electron groups bonding to atoms and 1 non-bonding group. This molecule has a shape resembling that of a triangular pyramid, and so it takes the name trigonal pyramidal. This image shows how the lone pair strongly repels the bonding pairs and pushes them down into this pyramidal shape. The general representation of this shape is shown here, with the E again signifying a lone pair of electrons. An example of a trigonal pyramidal compound is ammonia. Ammonia now has angles greater than 109.5 between the non-bonding group and the bonding groups, and angles of 107.5 between the bonding groups. Remember, the angle of 107.5 is smaller because the bonding groups are being pushed closer together by the strong repulsion of the lone pair. The last possible shape, with 4 electron groups, has 2 of those groups bonding to atoms and 2 non-bonding groups. This gives the molecule a bent shape. Many call this shape angular or V-shaped to differentiate it from the bent shape that has 3 electron groups. These images show how the 2 lone pairs point as far away from each other as possible and cause the bonding pairs to point downwards. If you were to remove the 2 lone pairs, you can see how the bonding pairs take on this angular or V-shaped structure. The general representation of this shape is shown here, where again the electron groups are pointing away from each other to the back of the page and towards you. An example of an angular or V-shaped compound is the azonide ion. This compound has angles that are greater than 109.5 between the non-bonding groups and angles of 104.5 between bonding groups. The next geometrical arrangement is of 5 electron groups and takes the name trigonal bipyramidal. There are 4 possible molecular shapes for this geometrical electron group arrangement. The first has all 5 electron groups bonding to atoms. To ensure that the 5 regions of electron density are pointing as far away from each other as possible, the atoms are arranged like 2 triangular pyramids stacked together base to base, and hence the name trigonal bipyramidal. This image shows the orientation of the 5 regions of electron density. You can see the formation of 2 triangular pyramids stacked together base to base. The general representation of this shape is shown here, and an example of a trigonal bipyramidal compound is phosphorus pentafluoride. This compound has 90-degree angles between the bonding groups in the x-axis and the y-axis, and it has 120-degree angles between the bonding groups in the x-axis. The second possible shape has 4 of the 5 electron groups bonding to atoms and 1 non-bonding group. This causes the molecule to resemble a seesaw. This image shows how the electron groups arrange themselves into this very distinct orientation. The bonding groups protruding downwards resemble the base of the seesaw, and the bonding groups pointing in opposite direction are the rod of the seesaw. The general representation of the shape is shown here. This ball and stick model really does show how this molecule looks like a seesaw. An example of a seesaw compound is sulfur tetrafluoride. This compound has angles that are greater than 90 degrees between the non-bonding group in the y-axis and the bonding groups in the x-axis. It also has an angle that's greater than 120 degrees between the lone pair and the bonding pairs pointing downwards. And of course, because of that, we now have an angle that is less than 120 between those 2 bonding groups because of the stronger repulsion of the lone pair. The third possible shape with 5 electron groups has 3 of the 5 bonding to atoms and 2 non-bonding groups. This causes the molecule to take on a T-shape. This image shows how the lone pairs force the bonding pairs into this T-shaped orientation. The lone pairs pushing outwards cause 2 of the bonding groups to take on this linear structure, and the third bonding group to protrude outwards, creating this T-shape. The general representation of these shapes is shown here. An example of a T-shaped molecule is iodine trichloride. This compound has an angle that is greater than 120 degrees between the 2 non-bonding groups, and angles that are less than 120 degrees between the non-bonding groups and the bonding group in the x-axis. It's important to note that there's a great deal of repulsion happening here because of the two lone pairs pushing against each other. The 90-degree angle occurs between the bonding group in the y-axis and the bonding groups in the x-axis. The last possible shape has 2 of the 5 electron groups bonding to atoms and 3 non-bonding groups. This causes the molecule to be linear in shape. This image shows how the lone pairs arrange themselves around the bonding pairs that are facing in opposite direction. The general representation of these shapes are shown here. An example of these linear compounds is the triiodide ion. This ion has 120 degrees exactly between each one of the lone pairs. And of course, this makes sense because in the x-axis, they're all pushing against each other with an equal amount of repulsion, causing them to be equidistant from each other. There's 180 degrees between the bonded atoms on either side of the central atom, creating this linear structure. The final geometrical arrangement I'll be covering consists of 6 electron groups and takes the name octahedral. Although there are 5 possible molecular shapes for this geometrical electron group arrangement, I'll be covering the main 3. The first has all 6 electron groups bonded to atoms. The name of this shape is octahedral because the electron groups arrange themselves into a structure that has 8 sides. This image shows the orientation of the 6 regions of electron density into this octahedral structure. The general representation of this shape is shown here. An example of an octahedral compound is the hexafluoroiodine ion. This ion has exactly 90 degrees between all of the bonding groups. The second possible shape has 5 of the 6 electron groups bonding to atoms and 1 non-bonding group. This causes the molecule to resemble a square-based pyramid, and so the shape is called square pyramidal. This image shows how the electron groups arrange themselves into this square-based pyramid. The lone pair pushes up against the bonding groups to create this planar structure, and one of the bonding groups protrudes upwards into this triangular shape. The general representation of these compounds are shown here, and an example of a square pyramidal compound is iodine pentafluoride. Now, because of the lone pair, we do have an angle that is greater than 90 degrees on the base from the lone pair of electrons to the bonding pairs in the x-axis. And we have 90-degree angles exactly between all of the bonding groups in the x-axis. And of course, we have an angle less than 90 degrees between the bonding groups in the x-axis and the bonding group in the y-axis because of the push upwards by the lone pair. The last shape with 6 electron groups has 4 of the 6 bonding to atoms and 2 non-bonding groups. This gives the molecule a flat square shape, and hence it is called square planar. This image shows how the 2 lone pairs are pointing in opposite direction and causing the bonding pairs to take on this planar shape. The general representation of this shape is shown here, and an example of a square planar compound is the tetrachloroiodine ion. This ion has 90 degrees between the non-bonding pairs and the bonding pairs in the x-axis, and 90 degrees between all of the bonding pairs. Again, you have these exact angles of 90 degrees because both lone pairs are repelling each other and repelling the bonding pairs with the exact same amount of force, which causes these bonded pairs to take this flat planar structure. Let's look at a few examples together and walk through the process of how we're to draw these VSEPR shapes and then identify their VSEPR names. The examples I have here are of methane, ammonia, and water. the first thing we need to do is we need to draw the Lewis structure. So that is the Lewis diagram for methane. That is the one for ammonia, and that's for water. The next thing I need to do is I need to count up the bonding groups and the non-bonding groups. By identifying how many bonding groups and non-bonding groups I have, I can then classify which geometrical electron group arrangement this molecule belongs to, and then which molecular shape it has. And so methane has 4 bonding electron groups, and so it has 0 non-bonding. Ammonia has 3 bonding and 1 non-bonding. And water has 2 bonding and 2 non-bonding. And so at this point, it should be clear that all 3 of these compounds actually belong to the tetrahedral geometrical electron group arrangement. But the first one is the only one that's going to take on the tetrahedral name. And it's going to take that name because all of the 4 electron groups are bonding into the same type of tripod structure. Ammonia, on the other hand, will have a trigonal pyramidal structure, where one of the lone pairs, as we discussed earlier, is going to push down on 3 bonding groups into this pyramidal structure. And water, well, water is going to have that angular bent shape, or that V shape that we showed, okay? 2 of the lone pairs are going to be pushing away from each other and causing the 2 bonding pairs to squeeze together into this bent or angular structure. VSEPR theory can also be used to predict the 3-dimensional structures of complex substances that have more than one central atom. The procedure for drawing such structures is to predict the electron arrangement around each central atom individually, and then combine these arrangements to predict the overall structure. An example of this would be methanol. This slide and the next 2 slides are summary tables that amalgamate all the information discussed in this lecture. These tables show all the geometrical arrangements of electron groups and the molecular shapes they can create. These tables will be very helpful to you when doing practice questions. The entirety of VSEPR theory was proposed to understand the shapes of molecules and how they may connect together to react. But of course, it's very important to also understand molecular polarity. It's because of molecular polarity that these compounds may be drawn together in the first place to react. When atoms of 2 different elements have differences in electronegativity between 0.5 and 1.6, the bond between them is considered polar covalent. An example of this would be hydrogen chloride. Now, we're very familiar with the dipoles that are placed here on top of hydrogen chloride, but many have never seen this symbol before. That symbol is a vector. The vector is used to represent the bond dipole and points towards the more electronegative element, with a cross on the tail to signify the positive pole it leaves behind. For a diatomic molecule, such as hydrogen chloride, the bond polarity is also the molecule's polarity. But for polyatomic molecules, that is, molecules with more than 2 atoms, the molecular polarity depends on the polarity of all the bonds in the molecule. An example would be carbon dioxide. Carbon dioxide has 3 separate atoms, forming 2 bonds. Carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. The difference is 1. So each one of these bonds is quite strong, creating their own polar vectors. Carbon dioxide is a symmetrical linear molecule with polar bonds. Due to the linear shape of this molecule, the polarities of the 2 bonds are directly opposite to each other. The 2 bond polarities exactly counteract each other. And so carbon dioxide, although it has 2 polar bonds, is actually a non-polar molecule because the vectors are canceling each other out. The pull on one side is exactly counteracted by the pull on the other. The shape of a molecule combined with the polarity of its individual bonds determines its polarity. Let's compare two molecules with the same molecular shape: carbon tetrachloride and trichloromethane. When you look at these two compounds, it becomes clear that both of them are tetrahedral in shape. Yet one of them is nonpolar while the other is polar. It seems like the only difference between these two compounds is that this central carbon atom is bonded to a hydrogen atom instead of a chlorine atom. Ironically, this carbon-hydrogen bond is nonpolar, and so the addition of a nonpolar bond to this compound has made it polar. How does this make any sense? Well, if you look exclusively at the bonds that make up this compound, it's very difficult to explain this phenomenon. A bond between carbon and chlorine is polar because the difference in electronegativity between these two elements is 0.5. And so carbon tetrachloride has 4 of these polar bonds and yet is nonpolar. A carbon-hydrogen bond, on the other hand, is nonpolar because the difference in electronegativity is 0.4. And so trichloromethane has 3 polar bonds and 1 nonpolar bond and is polar. So how do we make sense of this? Well, the major difference between these two compounds is really their symmetry. One compound is symmetrical while the other is asymmetrical. Carbon tetrachloride is a symmetrical molecule with 4 bonds that are exactly 120 degrees apart. Not only that, but the carbon bonds are all to chlorine atoms. And each chlorine atom is attracting electrons from the carbon with the exact same amount of force. The attraction of this chlorine pulling downward is completely cancelled out by this chlorine pulling upward. And the magnitude of attraction of this chlorine pulling to the left is exactly counteracted by the attraction of this chlorine pulling to the right. And so each of these polar vectors cancel out, causing this molecule with 4 polar bonds to be nonpolar. Trichloromethane, however, is asymmetrical. Because of this 1 bond to hydrogen, the attractive pull of the chlorines do not cancel out. Although this chlorine pulling to the left is still neutralized by this chlorine pulling to the right, the chlorine dragging the electrons downwards does not have an attractive force to counteract it in the upward direction. And because of this, the entire molecule is polar because it has a single dipole. This vector shows the overall movement of electrons for the entire molecule. For quick reference, I've included this table which shows the polarity of some of the key molecular shapes that we've discussed in this lecture. And with this slide, I conclude this package. I hope you understood all the concepts I discussed in today's lecture, and all the best.